Hi there and welcome to this video for Senior Physics on Electromagnetism and Electricity. In this video we're going to continue our exploration of electromagnetic induction. We're going to use a PhET simulation to basically run through Faraday's law and hopefully put a few more concepts in place and help your understanding. This will also then link with a practical video which will show the same sort of process happening in reality. Okay, so let's just recap that Faraday came up with the algorithm EMF equals delta psi over delta T, where EMF was the electromotive force, or the force generated on electrons, causing them to move through a conducting rod. Now, basically, he worked on the principle that as we moved from large density to low density, or low density to large density, over a certain amount of time, a voltage would be generated. And I ran through this diagram that you can see below, where A was basically the area, a certain area moving to an area B through the magnetic field lines. And you can see that the field lines are changing from 7 on the left in A to 3 on the right in B. This change in number of field lines, or change in flux, was also termed voltage. So basically what we're going to do is use the link that you can see below. I will also put the link up on the post so that you can actually have a play yourself. So let's load up the file. So I'm just going to, here we have our simulation, and you can see the link above. Now I'm only going to use one coil in this case. So basically what I've got is a coil, okay, which is then linked to a bulb, and it's also linked to a voltmeter. So what I can do is I will take my magnet, and using my magnet I will slowly pass it through the coil. And you can see the needle of the voltage basically changing. Now as soon as I stop moving my magnet, I get no current. Now remember that this is because when you stop moving, you've only got one magnetic field, the field of the magnet. Remember, it doesn't matter whether I move the magnet or the coil and the magnet, because the two are working, it's all relative to each other. So relative to the magnet, the coil's moving over it. Relative to the coil, the magnet's moving over it. So it really doesn't matter. The fact is, over the field lines, what we're going to be doing is, if we've got charge which is moving, will generate a magnetic field in the solenoid, and that will interact with the magnetic field of the magnet. Now remember, when I pushed north in, it went to the positive side. Now it's stopped at 0. Look what happens when I pull it back out. Okay, it goes in the opposite direction. Now I pulled it out quickly. You saw the light flash. The light flashed because I got a flow of current, because the electrons had energy to move from one part of the circuit to another. As it flowed across the bulb, we saw that it moved in the opposite direction. So let's do it again. Let's push our north in, goes positive, and the light flashes. No movement once it's stationary. Pull it out, and we can see that it goes in the opposite direction. Positive, 0, negative, out. Positive, 0, negative, out. I do it slower, I get less of a movement, then back to 0, and again as I pull it out, do it slowly, and I get less of a movement. Let's flip the magnet and see what happens. So now I've got my southern end. Okay, let's see what happens. I push it in. This time it goes to the left, back to 0 when it's stationary, pull it out, and I get the same effect, but it's going to the right. Do it quickly, we get a massive movement. I'll just get it to 0 there. Pull it out quickly, massive movement in the opposite direction. So let's flip it back to its normal position. Okay, and let's put in the field lines. Now what you can see there in this case is you've got some field lines which are generated. I'm going to pull it all the way back here. So basically I've got, it's not going to work great, but I've got about 3 or 4 field lines acting in the solenoid. Now at the moment the magnet is stationary. If the magnet is stationary, yes, there's field lines, but there's no movement of the electrons. So the result is there is no magnetic field generated in the solenoid. But as soon as I start moving the magnet from right to left, you will see that the field lines will increase. As a result, we increase in field line density, or we increase in flux. If we increase in flux with time, remember the algorithm, delta psi over delta t. If I increase in flux or field density with time, I will generate an EMF. So let's see if it works. So here we go. We're going to move that north. Check the field lines as they start increasing. Okay, they're at maximum here. Pull it back out. It goes in the opposite direction. We are decreasing our magnetic field lines, and the result is we get less of an effect. Now let's do it quickly. Same thing. Pull it out quickly. Same thing. We're going from very large density to small density, or small density here to very large density very, very quickly. We flip the magnet. Actually, I'll pull it out first. Let's pull it out so it's completely... Now, if I flip the magnet, you can see now that the field lines have changed direction. So obviously, if the field lines are changing direction, the force is going to be changing direction. So the result is, instead of the force pushing this way, it's now going to push in the opposite, and vice versa. So let's have a go at pushing our field lines in. Do it slowly. Whoops, run out of space. So I'm going to increase my magnetic field lines, still get a voltage which is generated. Pull it out, go from large density to small density, and it goes in the opposite direction. Do it quickly, and coming back out the other way. Fine, so again, we'll do it quickly again, push it in, pull it out, and the result is we're going in that opposite. Now, obviously, if I pull all the way through, watch what then happens. Keep going and pulling it through. Now, that's because we've got a change in field lines in this case. So as a result, it flips between the two. So in this case, the field lines are going out. I increase in density and then pull it out the other way, and it goes in the opposite direction. So we get the idea, back to zero, and this is what's happening as we're changing the direction of the field lines. Okay, so basically we could add a second coil if we wanted to. In this case, we would have less of an effect in this coil. Okay, you can see I'm doing the same thing, sort of similar speed. Do the same thing on this side, same speed, and we can see that we're going all the way to the bottom. Same speed, we're only going halfway. Same speed, all the way to the bottom. The reason being, I've got more coils in this case. Because I've got more coils in the bottom one, I can increase the EMF which is generated. Okay, well, I hope you sort of found that useful. I think it's a really good simulation. As I say, I'll put this link up for you to go and have a play with. Key concept is to try and understand why this is occurring and use the algorithm to help explain. Well, thanks for joining me on this video. Hope you found it useful, and I look forward to you joining me again. Thanks for watching.